Okay, I want to start you out understanding limits graphically and numerically first. So let's consider some functions here. So what I want to do, I don't really want to talk about limits just yet. I want to just talk about a function. If you were to graph this function, x squared minus 4 over x minus 2, it would actually be defined everywhere except at 2. If you try to graph it at 2, you'll actually get a hole right there at 2. So if you try to evaluate it at 2, you can't evaluate it. But basically, if you did graph this, it would just look like a straight line. Okay? Now, what's happening here? So here's what's happening here. You have x equal 2 is represented by this vertical line. So everywhere on that line, x is 2. So what we want to do is we want to see where this function, where the y value is going as we get close to 2. Well, if we approach 2 from this side, well, then basically what's going to happen is, just a second. Basically what's going to happen is this. So as we approach 2 from the left, the y value is going to get closer and closer and closer to a particular number. And if you want to see what that number is, well, then just look over here. You can see that that number is 4. So as x approaches 2 from this side, the y values get closer and closer and closer to this number 4. Well, also, if you were to approach 2 from the other side, like if you were to approach 2 from this side, well, the y values would get closer and closer and closer to 4 from that side. So the y values would get close to 4. So basically, as you approach 2 from either side, the function appears to approach this number, this y value, x equal 4. And so that's what we wanted you to see. Even though the function's not defined at 2, it appears that as x approaches 2, the function does approach a particular number, 4. Now, let's take a look at this one. This one, I want to look at this function, x cubed plus 1 over x plus 1, but I want to look at it at x equal -1 because that's where the function's undefined. So this vertical line represents the line x equal -1. Now notice, as x gets closer and closer to -1 from this side, notice that the y value here, like the corresponding y values, are actually getting closer and closer and closer to this horizontal line right here, which is at y equal 3. And then notice as we get closer to x from the right hand side, notice that the y values, the corresponding y values, get closer and closer and closer to that same number, 3. So here, this function appears to approach 3. The function, the y value, or f of x, appears to approach 3 as x approaches -1. Now, I haven't proved anything yet. We'll learn how to do that later. Right now, I'm just trying to get you to understand. Now, this function is kind of strange, but this one is square root of x plus 9 minus 3 over x as x approaches, well, we're going to look at it as x approaches 0. So, because the graph is undefined at 0. Well, notice that it seems like it flattens out here. But actually, if you took a picture of the entire graph, you actually wouldn't see, it wouldn't look exactly like this. But I'm just zoomed in on a particular area. But notice that if you approach 0 from the left, notice that it looks like the y value is right here. And if you approach 0 from the right, it looks like the y value is right there. So I would say that as you approach 0, as f of x approaches, or as x approaches 0, then f of x appears to approach this small number here. Now, based on these grids, I'm going to estimate that as 1/5. We'll find out later that that's actually not the true value. But so this is only an estimation. So I'm going to say it's approximately 1/5. Now this function here, I'm going to look at this function near x equal 3. So x equal 3 is this vertical line. So notice that if you approach 3 from this side, the graph appears to just continue to decrease without bound. And as you approach 3 from this side, the graph tends to increase without bound. So from that, notice that if the graph is increasing or decreasing without bounds, then it's not approaching a particular number. So in this case, f of x does not approach a particular number as x approaches 3. And we'll find out what that means is that the limit does not exist when we get into limits. Okay, let's take a look at another function. Okay, this function is y equals sine x over x, and we're going to view this function as x approaches 0 or near 0. Well, notice that this vertical line represents x equals 0, the y-axis. So if you were to approach 0 from the left, notice that the graph tends to get closer and closer to this y value up here. And then if you approach from the right, the y value still gets closer and closer and closer to the same number. Well, that number right there is actually the number 1. So f of x appears to approach 1 as x approaches 0, because as you approach 0 from the left, it's approaching this number 1. You can't really see it. Let me move this line there. You can see the 1. And so as you approach 0 from either side, the y value appears to be approaching 1. Okay, now here's another graph. This is absolute value of x minus 2 all divided by x minus 2. Now I'm going to view this one as near x equal 2. Well, x equal 2 would be right there. And so notice that as you approach 2 from this side, as you approach 2 from this side, I'm trying to draw straight lines there, but let me just do it this way. So as you approach 2 from this side, notice down here, the graph is down here. But notice that the graph stays right where it is. It never budges from -1. So down here, the graph's going to be -1. So if you approach 2 from the left, the y values are going to be -1. Now, if you approach 2 from the other side, well, now notice where the y values are. Now the y values are up here at +1. So basically what we found here is as you approach 2 from the left, the graph is -1, but as you approach 2 from the right, the graph is +1. Well, we can't say that f of x approaches a particular number because they don't agree on the number that it's approaching. So we're not going to get a limit as x approaches 2 for this one. And then I've got one more example I want to look at. I want to look at this function as x goes to infinity. Now, infinity, obviously, infinity means that we're going to a very large number. So basically, what you can do here is look as x gets large, and I've got that going the wrong way, but anyway, as x gets large, you're going to get, so as x gets large, notice the graph. The graph here sort of gets closer and closer and closer to this line right here. And this line, if you count up, you can see that's 1, 2. So that's 2. So this graph, as x goes to infinity, this graph appears to approach 2. Okay, so that's one way to get a handle on limits, is to look at the particular graphs. But I will tell you, you can't look at the graph and identify limits, and I'll show you why soon. So this is just these are just visual tools that help you understand what we mean when we say a function has a limit. Okay, now I purposely haven't introduced the notion of a limit yet, but let's go ahead and look at these functions in a table. Let's say we wanted to know what this function was going to do near x equal 2. Well, you know you can't plug 2 into this because you would get 0 over 0, and you can't divide by 0. So when I say NA, I just mean it's undefined. But if we were to approach 2 from, say, the left, well, then I would have to go through these numbers, 1.9, 1.99, 1.999, and so forth to get to 2. Well, if you'll just take your calculator and plug 1.99 in here, and then see what you get, 1.99 squared minus 4 over 1.99 minus 2, you'll get 3.9. And then if you do the same thing for 1.999, 1.99 squared minus 4 over 1.99 minus 2, you'll get 3.99. And then if you do it for 1.999, you'll get 3.999. So it appears that the closer I get to 2, the closer this y value is becoming to 4. And the same thing happens if you approach from the other side. If you plug in 2.1, you get 4.1. If you plug in 2.01, you're going to get 4.01. If you plug in 2.001 into the function, you're going to get 4.001. So it appears that that function is approaching 4. But again, we haven't proved that yet. Now, if you do the same thing for this one, remember it's undefined at -1, so you can't plug -1 in. But if I pick numbers to the left of -1, like -1.1, if I plug that into this function, I got 3.31. If I plug -1.01 in, I got 3.03. If I plug -1.001 in, I got 3.003. And then if you plug in numbers to the right of -1, like -0.9, -0.99, or -0.999, notice the values tend to get closer and closer to 3. Now, if you remember the graph of this function, when we looked at the graph of this one, it appeared to be getting closer to 4, and this one appeared to be getting close to 3. Now, let's look at this one. This one, we're interested in what's happening around 0. And again, you can't plug 0 in because that would give you 0 in the denominator. But if you plug -0.1 in, say square root of -0.1 plus 9 minus 3 divided by -0.1, you get 0.167. Well, if you plug -0.01 in and evaluate the function, you get 0.1667. And then plug this in, you get 0.16667, and so forth. And then you pick numbers close to 0 from the other side, and you get that recurring 0.1666 theme. Well, actually, 1/6 is 0.16667. So actually, if we calculate this limit, we're going to find out that the actual limit is 1/6, not 1/5. Okay, now let me quickly go over these other three, and then we'll move on to something else. Okay, for this function near 3, if you plug in 2.99 or 2.999, you'll notice the values get larger and larger in the negative sense. And if you approach from the 3 from the other side, 3.01, 3.001, notice the values get larger in the positive sense. The sine x over x, notice as you get closer and closer to 0 from the left or from the right, notice that the y values get closer and closer to 1. I mean, when you plug in 0.001 or -0.001, you pretty much have 1. That 0.9999998 is pretty much 1. And then the last one, last two rather, this one, if you plug large values in, the larger the values in, the closer this number comes to 2. Remember, a while ago when we let x go to infinity, we saw that it was getting closer and closer to 2. So you can see that that rings true here. And then this one, remember, as we approach 2 from one side, that's supposed to say 2. As we approach 2 from one side, we had -1, and as we approach 2 from the other side, we got +1. So you can see that that function seems like it does not agree on a limit as we approach from one side to the other. So anyway, you can read this. There are two ways that can be used to estimate a limit, but neither guarantees the result. So what we're going to have to do is move on to an algebraic approach that will allow us to actually prove that a limit actually does equal what we think it does.